Hello everyone, I am Samir Velankar and I welcome all of you to this third video on AVL tree. In this video, we are going to construct an AVL tree. Remember, AVL tree is binary search tree which is balanced from scratch. So let's take an example where we are asked to construct AVL tree using data 1 to 7. So the data given is simply in sorted order and this data has to be added in the AVL tree. So let's start adding or inserting. Let's insert 1 in the AVL tree, the first data. The first data will be obviously added as root node. Remember, we are simply creating binary search tree. So root node is going to store 1 and left of root and right of root will be null because 1 is not having any children till now. Now, after you insert 1 in your tree, you ask, is this tree balanced? Of course, it is balanced because there is only one node in the entire tree. It is obeying the rule HL minus HR should be less than or equal to 1. So you proceed. As the tree is balanced, you proceed to insert 2 in this tree. Now, 2 in the existing tree will obviously go to the right of 1. And the tree is 1 is the root, 1 is the root, and 2 is right child of 1. Now, even this tree is balanced because if you check from bottommost level, 2 is perfectly balanced, left and right height of 2 is 0, and 1 is also balanced because left height is 0 and right height is 1, giving difference of 1, which is allowed. So, as this tree is balanced, we go further and we insert 3 in this tree. By inserting 3, we mean that 3 will go to the right of 2 because it is largest till now. Now you will see from bottom up, if you check bottom, isn't it, nodes, 3 is balanced, 2 is balanced because 2 has left height 0 and right height 1. So 0 minus 1 gives difference of 1. But 1 is not balanced. See, this root is not balanced, isn't it? Because the left height of root is 0 and right height is 2. So the difference between the left height and right height of 1 is 2. So which case is this? This 1 is not balanced due to right case. Yes, it is very much visible. So how do you handle right case? To handle right case, you simply rotate the node which is not balanced. Who is not balanced here? 1 is not balanced. Simply rotate that unbalanced node 1 to the left. So after rotation, what we get is 2 will take up the place of 1 and left of 2 will become 1. Yeah, 1 was rotated to the left of 2 and 3 will be right child of 2. As usual, 3 was anyway right child of 2, it remains right child of 2, isn't it? And now 1 and 3 are leaf nodes, observe, and 2 becomes the new root. Yes, root has changed, and surely the existing tree we are having is balanced. So the point to be explained here is while constructing AVL tree, whenever we insert any new node when we insert that node using usual binary search tree algorithm using less than greater than nodes. We first insert the node. And after inserting the node, we will check whether the tree is balanced or not. If the tree is balanced, fantastic. Let's then go ahead to insert next node. But after inserting a new node, if the tree is not balanced, then we first of all check which node is not balanced from bottom up. And once we know the node which is not balanced, the second thing which we check is why it is not balanced, due to which case. And we will find one of the cases out of the 4 which we saw in the earlier video, and then accordingly we will use rotation algorithms and balance it. Okay, let's go further. Let us now insert 4 in the latest tree. Let's insert 4. Now you know that the latest tree is 2, left child of 2 is 1, right child of 2 is 3. Now, where will 4 go? By the way, 2 is the root. Now, 4 will go to the right of 3. Usual binary search tree insertion, isn't it? Is largest. So, goes to the right of 2, right of 3. So, 4 is the right child of 3. Now, question out. After inserting 4, do you see that the tree is balanced? Yes, of course, this tree is balanced. Because from bottom level, 4 is balanced, 0 minus 0. 3 is balanced, 0 minus 1. Check the left height is 0, right height is 1. So 3 is balanced. 1 is anyway leaf, 1 is balanced, 0 minus 0. And 2 is also balanced because left height of 2 is 1 and right height of 2 is 3. Oh, sorry, right height of 2 is 2. Sorry, 2 levels to the right of 2. So this tree is balanced. I hope you are understanding. Then we just have to insert next value 5. Now 5 in the existing tree, this is the existing tree I am having. 5 will go to the right of 4. Now if you check from bottom up, 2 is still the root. From bottom up if you check, 5 is balanced, 0 minus 0, 4 is balanced, left height is 1, left height is 0, right height is 1. But 3 is not balanced from bottom up. So find out the first culprit from the bottom. Please try to understand. And 3 is not balanced because the left height of 3 is 0 and right height of 3 is 2. Observe 2 levels to the right of 3. So the balancing factor is disturbed here, isn't it? But why is 3 not balanced? 3 is not balanced because of right case. It is very much visible. You see this. 3 is not balanced because of right case, isn't it? So how do you handle it? You simply rotate 3 to the left of 4. So now the tree we get is 2 is still the root. There is no change up there. Left of 2 is still 1. There is no change here either. But 4 takes up the place of 3 and 3 goes to the left of 4. And 5 remains right child of 4. Right child of 4 was already 5. It remains 5. Now see the transform tree here. Check thoroughly that this tree is balanced. It has to be balanced. That rotation algorithms are like that it will keep the tree balanced. If you check from bottom level, 3 and 5 are balanced perfectly. Leaves 4 is balanced. 1 minus 1, observe. This is too good, too good. 4 is balanced. 1 is a leaf, so it is balanced. And what about the root node 2? What is the left height of 2? Left height of 2 is 1, only one depth at the left. And what is the right height of 2? Right height of 2 is clearly 2, isn't it? 2 depth on the right. So 1 minus 2 difference of 1 is allowed. So this tree is balanced. So after inserting 5, let's now insert 6 in the tree. Now, how will you insert 6? Usual insertion algorithm. Currently you have the tree like this. 4 is to the right of 2 and 3 and 5 are the children of 4. Now 6 will go to the right of 5. No need to explain why it goes to the right of 5. You know insertion algorithm of binary search tree. Now if you check this, very interestingly, while inserting 6, the tree is not balanced. Now have patience and you listen to what I am telling with immense concentration, because now we are coming to the major point and it seems that now you will understand how to balance a tree, because all the earlier cases were so simple, isn't it? Now just tell me, or rather tell yourselves, is this tree not balanced? Yes, it is not balanced. Due to whom? Due to 2, that is root. Check from bottom level. 6 is balanced. It is leaf. 5 is balanced. Just difference of 1 between left and right. So allowed. 4 is balanced. 4 is balanced. Because difference of 1 minus 2 levels at the right is allowed. 1 is anyway leaf. All these nodes are balanced. But check the root node now. Check this. 2. What is the left height of 2? Just 1. 1 level to the left. But to the right, if you see, right of 2 has 3 levels. Just see, there are 3 levels to the right, isn't it? Yes? Are you understanding? 3 levels to the right. So 2 is not balanced. But then 2 is not balanced due to which case? Now there is such confusion over here in the classroom. When I teach this, students often say, sir, this is which case? We are not understanding. We agree that 2 is not balanced, everybody says, due to difference between heights is more than 1, but we are not understanding the case. It is so easy to check the case is that first of all, why did 2 become unbalanced? Come again? Why is 2 unbalanced? 2 is unbalanced because you inserted 6. Come on, isn't it? Why did 2 become unbalanced? Because just now you inserted 6. What if you did not insert 6? Then that 2 was balanced in the earlier tree. Repeating it, 2 is not balanced because we have inserted 6. Now to check the case, why is 2 not balanced? Is you simply go from 2, keep an eye on node 2 and try to go from this node 2 towards 6 because 6 was inserted, right? So how will you go from 2 to 6? Come on. For going from 2 to 6, you will take right, correct? And once you reach the right child, that is 4, you want to reach 6, right? So you will again take right, isn't it? What am I explaining? Come on, I am trying to explain that to reach this new node 6 from the unbalanced node 2, 2 is not balanced, you will have to take right and then again right. That's it, that's it, that's it. That means the case is right, right. You just have to go 2 levels down towards the direction of the new node from the unbalanced node. 2 was not balanced due to 6. You inserted 6, isn't it? That's why 2 is not balanced. And you want to know the case. Then case can be known simply by traversing from 2 towards 6. Travel from 2 towards 6, but travel only 2 levels. So to go from 2 to 6, you will have to take first right, reach 4, then again right, reach 5. That's it, that's it. Stop here and you can say that the rule is right, right. Now, when I ask this in classroom, many students say that, sir, the case is right, right, right. Oh, but there is no such case, isn't it? So you just don't have to go all the levels down towards 6. You just have to traverse 2 levels and spell out. I mean, just speak out loudly. What is the direction in which you are going? If you go from 2 to 6, you are taking right 2 times, then the case is right, right. Okay, all right. So how do you handle right, right case? It is so easy. Whoever is not balanced, 2 is not balanced, simply rotate it to the left. That's why I said you concentrate here. 2 is not balanced, isn't it? So how do you handle right, right case? Whoever is not balanced, that is 2 is not balanced, rotate it to the left. So 2 will become left child of 4. Check this. 4 will now have left child 2 because 2 was rotated to the left of 4. But hello, 4 already had left child 3, isn't it? Where will that 3 go now? Are you observing? 4 already has left child 3. But it seems that we have lost 3. We have cut that 3 because 2 should come to the left of 4. We want to do the left rotation. Okay. And by the way, who is the right child of 4? Right child of 4 was 5. Check the earlier tree, it will remain 5. And right child of 5 was 6. It will remain 6. And what about left child of 2? It was 1. See the earlier tree, it will remain 1. There is no change to the left child of 2. But in this entire event, we have lost the node 3. We have lost it because 2 was to be rotated to the left of 4 and we have taken 2 to the left of 4. But left child of 4 was 3 and we have lost it. So what we do after doing all this process, we insert 3 again in the tree and you know that 3 will go to the left of 4 and 3 will go to the right of 2. Usual insertion algorithm of binary search tree. Now you observe the tree that we have is indeed balanced. You check it that all the nodes obey the rule and root is 4. All the nodes are obeying the rule left height minus right height should be less than or equal to 1. Just check this. Take your own time over here. See this? The tree which we had, I don't mind it drawing again. The tree that we had here was 2, 1, 4, 3, 5. And we inserted 6, isn't it? Now, what happened is after inserting 6, 2 got unbalanced. 2 was unbalanced. So we know that 2 is unbalanced, but it is so important to find out the correct case. Look, if you don't find correct case, whether it is left, left, right, 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 left, left, right, if you find it incorrectly, then you will do incorrect rotation, isn't it? And incorrect rotation will give you incorrect binary tree, which will not be balanced. So we know that 2 is not balanced, but to check out the case, you just go from 2 towards 6 because 6 is the new node you inserted. So from 2, you go towards 6 and read out loudly what are the direction you are taking. If you are going from 2 to 6, you will take right and go to 4, and you will take right and go to 5. So the case is right, right. That's it. Case is right, right. And if it is right, right case, then whichever node is not balanced, 2 is not balanced, is rotated to the left. So 2 takes over this node, isn't it? So 3 is lost and 2 becomes left child of 4. But then don't worry, we will insert 3 again in the tree using your usual algorithm, insertion algorithm. And now we have a binary search tree which is balanced. Okay. Now let's try to insert 7 in this latest tree. Last value, isn't it? Let's insert 7. So the latest tree we have is 4 is the root. And we have 2, 1, 3 here in this branch and 5, 6. Now 7 will be inserted to the extreme right, it is largest. But if you check from bottom up, 5 is not balanced. This is easy now. 5 is not balanced due to right, right. So 5 will be rotated to the left of 6. So the tree we have is now 4 is still the root. To the left branch we have 2, 1, 3. And to the right of 4 we have 6. But left child of 6 is 5 and right is 7. This is the tree we have, isn't it? And 4 is the root. Oh, look at this. I mean, dear students, just look at it. I mean, what a tree. What's so wonderful about this tree? We have inserted 1 to 7 and we have got perfect balanced tree, isn't it? So, what's so nice? Searching will be faster because this data structure is fat. Those who have come from B tree and B plus tree, watch that video. In that video, I said that the data structure, if it is fat and wider, and rather it is shallow, the data structure is not very deep, it is having very less levels from top to bottom, then such data structure is very good in searching. Now you tell me on an average, how many comparisons you will have to do to search any node? Let's say you are searching 7, then 7 is not at root, but you will take right because 7 is larger than 4. But 7 is not present at this 6 also. So you will take right and you get 7. But how many comparisons did you do to search 7? 3 comparisons. First comparison with 4, second with 6, and third with 7. Hardly 3 comparisons you did and you had 7 values, 1 to 7 in your data set. And you will agree that maximum you will have to do 3 comparisons only, not more than 3. Come on, you have 3 levels here. So where is the question of doing more than 3 comparisons come into picture? That's great, isn't it? What's so great about this is just imagine you did not know AVL tree at all. And data, I'm just writing it here, data given was 1 to 7. And you created simple binary search tree. So the binary search tree that you will create will be created somewhat like this, isn't it? 1, 2, 3, 4, 5, 6, 7. Oh, hello. All values are getting added to the right of every node, isn't it? And all the left pointers are null. Now you watch, this binary search tree looks like a linked list. I mean, where is the binary nature? Where is the binary nature here? Isn't it? That means 2 legs, left and right, are not balanced. If it is not balanced and only 1 leg gets stretched, then the searching becomes very slow. Look, this is also binary search tree, no doubt about it. And the above tree that we have drawn is also a binary search tree, no doubt. But which one is better? The better tree is the one which is balanced. That is AVL tree, isn't it? Now, if you are asked to search 7 in this tree, if you are asked to search 7, you will keep comparing the values till you reach 7, isn't it? And you have already done 7 comparisons now, which is too poor, too poor. So that's the importance of balancing a tree. If the tree is balanced, you get a fatter tree, wider tree, and it is a shallow tree. It is not very deep. It's not thin tree. We don't want thin and tall tree. We need a fat tree which is shorter in height. Shorter in height means less levels. Less levels means less comparisons, isn't it? Okay, I think I have done enough justice in this video to tell you how to create AVL tree. Now we have a second exercise here. Construct AVL tree from 7 to 1, which we will solve in the next video. But I am sure that you know how to do this 7 to 1. Just to keep our discussion continuous, we will be solving this question in the next video. Thank you very much.